This is the five notes for Calculus 1. Up until this point, you've basically learned how to find the most elementary integrations. You had these very simple formulas in terms of just finding antiderivatives of powers and trig functions and exponential, all of the functions. But just like when we were dealing with the derivatives, we were limited until we got to the chain rule, and then the chain rule opened up a whole sort of spectrum of more problems that we could do. Now we're in the same boat. So we're now going to approach problems that essentially where they were derivatives found from the chain rule, and now we have to go in the other direction. So what rule is that? We call that the substitution rule. Okay, so the substitution rule can be utilized both with indefinite integrals and definite integrals, both types. In this lesson, you will learn how to do so with both types. It'll be split into two pieces. Again, this is a very powerful lesson just because when you move on to Calc 2, if that's where you're headed, you will need to know this inside and out without any issues at all, almost like adding or subtracting. Moving on to the next level of math. You have to know this for moving on to the next level. So the substitution rule is very similar in strategy to the chain rule. If you remember the chain rule, it was all about identifying the inner function. So again, there's going to be some type of composition of functions, f of g of x, and the goal is to identify your g of x function, your inner function within that actual equation, and what you're going to end up doing with that inner function is taking the derivative of it. So what does that mean exactly? Well, if you look at the formula right here, you'll see that what I'm going to be doing is I'm going to be taking the antiderivative of some composed function like this. But it will turn out that the derivative of the inner function will also be present in some form, and this will allow us to complete the structure of it and actually be able to find the indefinite integral or the antiderivative. So it's extremely difficult to really portray that unless you're doing examples, but what I will say is that the procedure for doing so is right here. It is useful, but it will mean absolutely nothing to you unless we're going through and doing examples. All right, so just a note here. We are going to first start with the most basic substitution rules. So basically what I'm saying here is that we will first try some problems where the substitution works flawlessly. So what I mean is it's going to be a perfect substitution. It's not usually going to be that. It's just for the beginning problems to get you started. But also, big reminder here, remember that when we made the jump from indefinite to definite integrals, we went from using plus c for indefinite to evaluating for an area for definite. So now we've made our way back to the indefinite integrals, so that means we have to remember the plus c at the end of every one of our problems. So let's get started and work through a ton of examples. Okay, the first goal of any integration is if you can somehow identify an inner function. You should be experts at this by now via the chain rule when we did derivatives. But if you can identify an inner function, that is always going to be our substitution. So what does that mean? So we always let u equal to our inner function. Okay, so u is equal to our inner function. So essentially we're replacing that in the original function itself. So if you look really close, what we're going to do next is we're actually going to take the derivative du of, it's actually du dx, of this right here. So let's say we want to find du dx of that, we would get 2, right? But if you look at this closely, if we multiply both sides by dx, dx, then we're going to get du is equal to 2dx. This is actually what we want. Pretty soon we're just going to be skipping this step, but for now I want to show it so you understand that this is going to end up being what you get. Now, why is this important? So what you're going to do basically is you're going to be solving in each one of these problems for dx. So why are you doing that? Because dx is actually in our problem, and the goal of a substitution is to turn all of these functions from x variables to u variables. Well, we've already replaced 2x plus 1 with u, so hypothetically, this is gone. So now we have to replace dx. So dx is actually going to be equal to du over 2. Okay, or in other words, 1/2 du when we divide both sides by 2. So look what we have right here. So I'm just going to point it out. So right now we can take this value here and we can put it right there. And we can take this value here and put it right there. Okay, so that's our next step. So what does that look like? So that's going to be equals the antiderivative. We're going to bring the 2 down because nothing happened with the 2. We now have u cubed, and we now have 1/2 du. You can clearly see that this is all multiplication all the way through, and that the 1/2 and the 2 end up canceling each other out, and you end up with just u cubed du. All right, why was this so excellent? Because if you look at the shape of our problem right now, we could not have integrated what we're looking at here. But look at what the u substitution actually got us. It got us a perfect integrable function. If we integrate u cubed, we get u to the 4 over 4 plus c. Okay, so now this is one step away from the answer. Why is it not the answer? Because if we get a problem in terms of x, then we have to end the problem in terms of x, because if I say, hey, the antiderivative of 2 times 2x plus 1 cubed is u to the 4th over 4, it doesn't make any sense. They didn't give us a u. We're using u to manipulate the problem and make it easier to integrate, but now we have to go back. But what's really neat, don't we already know what u is? Put it back. 2x plus 1 to the 4th over 4 plus c, and that is the answer to our problem, or in other words, it's the antiderivative of this function. Now, so in the beginning, some students are a little bit thrown off just because they're like, okay, I got to do derivatives in integration problems. And yes, it does lead to some issues along the way for students in mixing them up. But this is an incredibly good this substitution is incredibly good at breaking down functions that were originally found by derivative using the chain rule, and this is it. Now, note, just like we've seen before, if you want to know whether this is right or not, all you have to do is take the derivative of it. So even though you don't have to do this for the problems, I'm going to do it right here. So if we do the derivative of, I'm going to bring the 4th to the front here, 1/4 2x plus 1 to the 4th plus c. Remember, this guy just goes out here, and we take the derivative of 2x plus 1 to the 4th. So what do we get? So the 4th comes out. We take the derivative of this, which requires the chain rule. So 4, 2x plus 1 to the 3rd, times the derivative of 2x plus 1. And then, of course, the derivative of this is just 0. So this is 2. If we multiply this out, 1/4 of 4 is 1, and then this 2 comes to the front, and we get this as our result. And look, we get the same thing. So you can always check your work when it comes to these problems to get where you need to go. It's actually very useful. Do you need to do that? No, it's not part of the answer to the problem, but it's extremely useful. So we're going to do a ton of these problems, all types, shapes, and sizes, because the best way to learn it is with practice. Okay, moving on to another problem. So even though if the last problem might have been a little bit crazy for you, just stick to the strategy. So again, what are we looking for? We're looking for where the inner function is located. Well, the inner function was usually located in parentheses or an exponent. So here it appears that what we're looking at is u being equal to our inner function 10x plus 5. Okay, so what we want to do is we want to take the derivative. So what I said before is we can pretty much skip this step and go right to this one. So what does that look like? So we would say du is equal to whatever the derivative of this is, which is 10, and then we're just going to plop a dx on it. So what that does is that gives us two equations we can use in order to manipulate our problems. So right now, if you look really closely at our problem, the exponent has become u. But we still have this dx sitting here that needs to be substituted for. So we're going to divide both sides of this here by 10. So what do we end up getting? We end up getting du over 10, or 1/10 du. Doesn't really matter too much how you write it. So therefore, what we're going to do is we're basically going to replace all of those pieces in our integral. So we got this. We have the 10. We have e to the u, because this is now going to go, oops, that's not what I wanted to do. This is going to go right here. And then we have dx, which is 1/10 du, which is going to go right there. Okay, so note all the variables of x are gone and been replaced with u's. So what do we get? So if we cancel out, the 10's wipe out, and we are left with pretty much the easiest possible antiderivative computation of the antiderivative of e to the u du. Okay? So we know that that is equal to e to the u plus c when we take the antiderivative. Therefore, all that's left to do is to go back to the variable x. We already know that u is equal to 10x plus 5. So we're going to take that and we're going to put it right back. So we're going to get e to the 10x plus 5 plus c, and that is our antiderivative. So this process is different for sure, but it's something that is very manageable. Now, before, you might have remembered that I said we're trying problems where the rule works flawlessly. Well, why is it working flawlessly for this? Is that basically when you're done, everything cancels out perfectly, so you're left with just u and the function that's there. Eventually, that might not happen, or it definitely won't happen eventually, but I'm just warning you that these are problems where it does work out perfectly, but still worth doing the practice and going through all the problems. 3. This problem is a little bit different. So we have 6x plus 1 quantity of 6x plus 1 times the square root of 3x squared plus x, all dx. So it turns out that we have grouping symbols around two quantities, around the 6x plus 1 and around the 3x squared plus x. So now we have to start being strategic in what we're doing here. So we have to make u equal to a value that when you take the derivative of it, it's going to end up matching or somewhat matching with what's left over. So for example, don't write this down yet if you're writing with me. So let's say that I did u equals 6x plus 1. And I took the derivative and got du equals 6 dx, right? So that means this would be u, and then dx would be equal to du over 6, or 1/6 du. So if I plug u into here and this goes away, and I put dx as du over 6, is there any way to get rid of the x's and the radical that are sitting here with this method? The answer is clearly no. There's nothing that's going to cancel out those x's and make them u's, based on the substitution that I just did, which means that substitution is wrong. So what is the only other expression that actually is in there? In the radical, we have 3x squared plus x as our u. So what happens if we do du? We actually get 6x plus 1. Hey, look at that. Dx. Okay, so this is a whole nother story. So if we divide, we get du over 6x plus 1. And then all of a sudden, we have a much different scenario that we can definitely manage. So for example, what happens? So we have 6x plus 1 here. We have replaced u with 3x squared plus x, so root u. And we've replaced dx with du over 6x plus 1. If you look at this carefully, look at what happens. We have a perfect substitution, and we end up with just root u du left over. Remember that this is the same as u to the 1/2 du, but truth be told, we don't have to do that. Well, you know what? Let's do it. So u to the 1/2 du. And if we actually take the integration, we're going to get u to the 1/2 plus 1 over 1/2 plus 1, as we've done it many times before, plus c, which is going to give us u to the 3/2 over 3/2, plus c, which is going to be 2/3 u to the 3/2 plus c. The only thing left to do, therefore, is to make sure that we take our original u and plop it right back into where it belongs. So we're going to get 2/3 3x squared plus x to the 3/2 plus c as our result. And you don't have to change that back to a radical if you don't want to. That is perfectly fine as the result for our antiderivative problem. So this is basically the strategy you're going to use all the time. So looking at up here, I went through, sometimes you're going to do the wrong substitution. Who cares? You do a couple things, you're like, well, that's not going to work, and you just undo, and you go right back to doing another part, and there's nothing wrong with that. When you go to do it, it's going to match. Remember, these functions are actually created so they work out, which means there's not going to be a crazy problem where it's not going to work out. The purpose of them is that they do. So just realize that you might have to do a little bit of practice before you get somewhere, and, making sure it's right or wrong or checking, but eventually you'll get where you need to go. Okay, last problem is also going to hammer on the same point that I was just discussing. If you look at 4, you'll see that we have a rational function. We have a numerator and a denominator that are both polynomials. So therefore, the only option we have for a substitution is to pick either the numerator or the denominator. So that's where we have to go with this. For example, let's just say we pick the numerator, right? Again, we pick the numerator. We would get 3x squared plus 3, and what's this derivative? It's just 6x. Is the 6x going to help us with anything with this, in any way match this? It is not. So therefore, that cannot be the correct substitution. Let's try the other one, x cubed plus 3x, and hopefully you're already seeing that is going to be 3x squared plus 3, which is absolutely wonderful. Now, I just want to hit the pause button for a second. There is a higher strategy to this. I don't know if you noticed, but we had 2 options in both 3 and 4, and both times we picked the higher degree value to substitute. Well, why is that? Because when we take the derivative, anytime we take the derivative of a function, the degree lowers 1. So that means it makes sense that we're taking the higher degree, because whatever we're going to get as the derivative is going to be the lower degree one. So hopefully that helps a little bit with this in case you weren't following as well. But that is the main strategy in terms of finding these. So again, over here, we're going to divide both sides by this expression and get this as our value. And now we know in our expression that we have both x squared plus 3x and dx taken care of. So we can then substitute in for the rest. So we got equals. We have our 3x squared plus 3. We have that is over now u. And we have a dx that is equal to times du over 3x squared plus 3. Okay, if you look closely, it's a perfect match, and these guys are gone, and all we're left with is du over u. Okay, remember that's the same as 1 over u du. So hopefully by now the light bulb is just going off like crazy in your head, and you're going, I remember. This is the integration of this is the natural log of the absolute value of u plus c, which means all that's left is to take our original u and put it right back into the function. So we're going to get the natural log of the absolute value, x cubed plus 3x plus c. Alrighty, so that is essentially a good example of the most basic, I know some of you are like, really? Yeah, they are. The most basic substitution rule, indefinite integral substitutions. But in reality, these substitutions aren't always that easy, and they will often leave behind constants of some kind. So it'll never leave behind a variable because everything has to be u after you substitute over, but it might leave behind some type of constant. That doesn't mean it's super difficult. You just have to be on the lookout for it. Okay, so let's take a peek at the next one. So again, what appears to be the perfect inner function? It appears to be 3 minus x. So for argument's sake, let's say we did du is equal to the derivative of 3 minus x, which is 0 minus 1, which is negative 1, and then dx. If we want to solve for dx, we're going to just basically either multiply or divide by a negative, and we're going to get negative du. Okay, so we go back to our original problem here, and we start doing our substitution. So first things first, we know that u is equal to 3 minus x, so we can then move it in there and get u to the 10th. We also know that dx is equal to negative du. So we now can take that and put it there. So what are we going to get? We're going to get negative du. So what does that look like? Well, this negative, be careful, this is multiplication right here. It's not u to the 10th minus du. So technically it's like that, but I'm not going to put that there. I've never seen parentheses before when we do this. So just realize it is multiplication. This negative is essentially constant, so we're going to move it to the front, and we're going to get u to the 10 du. So then all we do is integrate from there. That should be the easy part. We're going to get negative, and then we're going to get u to the 11 over 11 plus c. And then the last part is to take our 3 minus x and put it right back in. So negative 3 minus x to the 11th over 11 plus c. And that is the antiderivative of our function. Moving on. Next problem, x to the 4th times x to the 5th plus 6 dx. Set up our substitution. We do have two functions technically. I know one is in parentheses, but when we do have two functions, what do we normally go towards or gravitate towards? We gravitate to times the one with the higher degree. So the higher degree one is actually x to the 5th plus 6. So what do we do when we find the derivative? We get du equals 5x to the 4th dx, and dx is equal to du over 5x to the 4th. All right, so we have our substitution set up perfectly, and we end up with the following. So our x to the 4th is still staying put. We substitute a u for our x to the 5th plus 6, and then our dx is du over 5x to the 4th. So if you look at this carefully, it looks like our x to the 4th is gone, and we are only left with u variables. So everything is good if that's the case, but worth noting, what we have is we have a 5 in a denominator over here, which means we have a constant of 1/5 that has to move to the outside, and then we're left with just 1/5 u du. If we keep on going with our antiderivative, we're going to get u squared over 2. 1/5 goes along for the ride, plus c, which is going to be u squared over 10 plus c. Only thing left to do is to take our original and plug it right back in. So we're going to get x to the 5th plus 6, quantity squared, over 10 plus c, and this is our antiderivative. And again, just to be clear, any one of these we can take the derivative of, and we will end up back at our original function. A side note on this specific problem, in the bigger frame of things, we actually did not need the substitution rule to do this problem. We could have just distributed this and gotten x to the 9th plus 6x to the 4th, and then just did straight antiderivative, and that's perfectly fine within what you do. That would work just fine, but I just wanted to point that out so you realize that that was a possibility. I often give these problems as examples because they're easy for students. So if it's most of the time, it's going to say use the substitution rule. So make sure you absolutely do that. Okay, so as we move forward here, the problems are going to get a little trickier. So just, make sure that you are, following along and you see the process, because that's going to be, for some students, it'll be a little bit more difficult to go through it. Now, just a note, hopefully your brain is already in this state of mind, but whenever I told you that there would be an exponent on a trig function, it's always ideal to rewrite that trig function as follows. So, for example, cosine cubed x is the same as cosine x quantity cubed. Why is it very nice to rewrite that? Because what it does is it gives you insight into what the ideal inner function is going to be for this problem, and that is going to be cosine x. Okay, so that is our inner function. Now, interesting side note about this problem is, hypothetically, you could have set either one of these equal to u, sine or cosine, and the derivative that you manufacture from your scenarios is going to end up matching the other one, the other function that's in it, because sine and cosine are derivative buddies, right? So it's ideal, again, always to tackle the one with the higher exponent involved. Will it always work out that way? No, but there are exceptions, but usually that's the best thing to do in the scope of the problem, at least when it comes to the basic substitution rule. Okay, so we have u is equal to cosine right now, and we want to solve for dx and get du over negative sine x. All right, so here goes our substitution. Antiderivative, we have cosine being replaced by u to get u cubed. And we have sine x not going anywhere. Then we have dx is equal to du over negative sine x. Okay, if you look closely, our negative sine x is going to cancel out, but there's actually going to be this negative sign right here that we cannot forget. That is a part of the problem. So that negative sign is going to shoot to outside the integral as a constant, and we're going to get u cubed du as our function for integrating. So let's do the integration. Negative stays. We're going to get u to the 4th over 4 plus c. And then the only thing left to do is to bring back cosine into the fold and get cosine x to the 4th over 4 plus c. If you want to change this to cosine 4th x, that's fine, but I'm perfectly fine with you leaving it like this, and that would be your answer to the problem. Let's take a look at the next problem, number 8. So I included this problem mainly because of its association with number 7. So obviously trig related, but it has to be accomplished in a different way. So in this problem, we were given two trig functions. And when we set one of the substitution u's equal to one of the trig functions, and the derivative gave us the other one, so we had a match. In this problem, we were again given two trig functions, but this time it's accomplished in a whole different way. And it's all based on your knowledge of derivatives. You knew when you looked at this problem, hopefully, that the derivative of sine is cosine and the derivative of cosine is negative sine, so you can go back and forth. That's not the case with this. The derivative of tangent is secant squared, and the derivative of secant is secant tangent, so there's something amiss here. So this is a problem that's much different, and what should really strike you as odd is the fact that these were a single variable x, whereas now we have a quantity within these. Now, it would make sense, hopefully, to most students that this should be the substitution, but students will still be sort of thrown by the secant tangent, but you shouldn't be. Why? Because we know that secant tangent is the derivative of secant. So if we take the derivative of secant tangent, it's a perfect derivative back to secant. So this should be something that should pop up right away in your heads. If you take the derivative of this 1 minus 2x, you're going to get negative 2 dx. And as always, we're going to divide. So this time, I'll just leave the negative 2 in the bottom of du. So here, what does that look like? Well, we're going to replace 1 minus 2x with u in both of these scenarios. So we're going to get secant u tangent u. Okay, so far so good. These guys are all gone. The only thing left is the dx that has to go right there. So we're going to get du over negative 2. So be careful here, this negative 2 is in the denominator, so when we move it out as a constant, it's going to be negative 1/2 secant u tangent u. The du stays put, and therefore we should easily be able to find the antiderivative of this, which is just secant u plus c. Then we have to take our 1 minus 2x, throw it right back in for u, and get negative 1/2 secant 1 minus 2x plus c, and that is our antiderivative. So when you look through these problems, there are going to be small things, and you're going to have to know your stuff, is the best way to put it. It's not going to be a super easy substitution all the time. You have to be able to play with things and be able to roll with the punches. Alrighty, so looking at some more examples. Number 9. If we need to set a u substitution for this one, there are two quantities, but you've been hopefully trained and understand that you want to set u equal to the higher degree polynomial. Okay, if you do so, you are going to get 8x minus 6 dx as your value, which means dx is equal to du over 8x minus 6. Okay, so if we move on and we do our substitutions, our u will end up in here, and then our du 8x minus 6 will end up here. So we get 4x minus 3, we get u to the 5th, and then we get du over 8x minus 6. At this point, you might be looking at this and going, uh-oh, it doesn't look like we have the match we usually get. But this is where things start to get a little tricky. You might need to look behind the curtain, so to speak, a little bit more. For example, if we bring this, again, u to the 5th, and du, 8x minus 6, doesn't that have a relationship to 4x minus 3? Hopefully you look at that and you go, wait a second, I could take out a 2 from 8x minus 6 and get a 4x minus 3, which means this does cancel out, but we just so happen to have a constant left over. So what do we end up with? We end up with a half coming to the outside, u to the 5th du, which is going to be a half u to the 6th over 6 plus c, which is u to the 6th over 12 plus c. And then the only thing left is we need to take our original function and throw it right back in. So we're going to get the quantity 4x squared minus 6x plus 7 all to the 6th over 12 plus c, and that is our antiderivative. Again, if we need to verify that this is equal to the original equation, we just take the derivative of it if you feel like you need to. Number 10 is the type of problem that really will give students the shakes. They'll look at this problem and go, what is happening right now? Yeah, so 3 sine of the natural log of x all over x times dx. Okay, so lots going on here. Doesn't look very fun, but the key is you want to follow your instincts. And hopefully your instincts in picking out an inner function will draw your eyes directly to what appears to be the only inner function in the problem, which is u equals the natural log of x. Now you guys know that the derivative of the natural log of x is 1 over x dx. So what's left? Well, in order to get dx by itself, we need to multiply both sides by x of this. So we're going to be left with x du is equal to dx. All right, we move on to our problem. We have a 3, interestingly enough, that is just going to go right to the outside in the beginning. It's a constant. It's just sort of hanging out there. We don't know why it's there, but it's hanging out, so we're going to move it outside. We have a sine, which isn't moving anywhere. The natural log of x converts to u, so sine of u. We have an x that's floating here, and then our dx becomes x du. All right, if you look closely, our x's cancel out, and we end up with 3 integral sine u du. We can then take our antiderivative. So the antiderivative of sine u, remember the formulas you learned were sine ax, not just, so when a is 1, we don't have to worry about the 1 over a in the front. We can literally just take the antiderivative of sine. But is there a function we can take directly to get sine, the derivative? No, because the derivative of cosine is negative sine. So when we go back, we also have to have a negative involved. So this is going to be negative cosine u plus c. If we simplify that, this is going to be negative 3 cosine u plus c. And the only thing left to do is to take our natural log of x, throw it back into our equation, and get negative 3 cosine of the natural log of x, natural log of x plus c. Doesn't look right here. Natural log of x plus c. So this is our antiderivative. The last 2 problems here I don't usually cover in class during summer sessions. What I'm going to do is I'm just going to give you the answer to them, and feel free to use them as extra practice if you'd like to go through. For the first one, you're going to get 15/8 times x squared minus 8x to the 4/3 plus c. For the last one, you're going to get 1/24 2 plus 4x to the negative 3 to the negative 6 plus c. These are, more crazy problems that deal with substitutions that are all over the place. But, as I said, these are great problems for extra practice for students if they want to go and make sure that they get the exact result that we're getting here. Okay, so this entire section 5.5 could be split up into 2 pieces. It could be 2 different sections, and in a lot of textbooks I've seen that. Why? Because the first part of what we've already learned is all about the substitution rule for indefinite integrals, which means you're trying to find the result in terms of what is the infinite family of derivatives that you can achieve by taking the antiderivative of a certain function. Now, what if we move on to the substitution rule for definite integrals? There isn't going to be too much of a change, but remember, when we move on to definite integrals, the plus c is no longer. We're looking for an answer that is actually a number area under a curve, and now we're going to have limits on our integral symbols, essentially, that we're going to have to analyze. Now, realize this is going to change the process. There's actually two ways to follow this process when it comes to definite integrals. I basically only cover one way. If you have learned this differently before, or you like a better way, you can use it. I'm going to be using my particular method that I'm used to. I made a point to show the two major changes that are a part of my method that I use. They are as follows. It says you must change the limits of integration a and b using your u substitution equation. Why would we do this? Because we're going to need the limits in terms of u and not x. So if you look at our problem here, we have b and a. Look what happens. We have g of b and g of a. So these are going to be your new limits of integration we're going to have to change to. Our other statement here says, do not substitute the u sub equation back into the problem as we did previously. Rather, you continue on and evaluate the antiderivative in terms of u. Okay, what does that mean? So in our problems, in every single problem we did, we took this and put it back in, hold on one second, put it back in for u. We're not going to need to do that any longer. Why? Because we're changing the limits of integration from x to u, so they're already going to be in terms of this function, so we can go ahead and just evaluate with u in mind instead of x. It's really hard for me to verbalize and for you to really get this without doing examples. So that's the best way to learn, and that's what we're going to do right now. Here we go. Follow the same method that you're used to. Identify the inner function and make it your u substitution. Then take the derivative, get 4 dx, then divide to get dx all by its lonesome, and get this as a row. If you want to do 1/4 du, that's fine as well. Doesn't matter which way you do it. Okay. So what does this mean? So in our next step, what we're not going to do is we're not going to write 1 and 3. So this is why I always say this is almost a whole new section, because we're now changing things up. We're not going to write that 1 and 3, and I'll show you why in a second. But we are going to continue and do what we normally do. So u goes here, we get u squared. And du over 4 replaces dx, and we get this. Okay, now, notice that every variable in my new equation is u, like it normally is. All the x's are gone. That is the key concept with this right here. So these variables here are x limits. We need u limits. So my question is there any equation that's perfectly set up to change any x's to u's? Well, hopefully you immediately see this equation right here. Oops, it didn't change over. I want the highlighter. There it is. You immediately see this equation right here and go, oh, okay. Can I take 1 and 3 and plug it into each one of those? And the answer is absolutely yes. So what I normally do is I create sort of an aside over here where I change the limits. For example, we first tackled the 3, so we're going to say u. So all we're doing is rewriting this, but we're doing it with each one of these in there. So u is going to be equal to 4 times 3 minus 3, which is going to give us 9. And our second u is going to be equal to 4 times 1 minus 3, which is going to be equal to 1. So we immediately change our limits to 1 and 9 instead of 1 and 3. So, by the way, just a coincidence that the 1s didn't change. So that is a very key step that students forget. If you forget that, you're done. I'm just going to tell you right now. So note, let's get back to our problem. This 4 is a 1/4 constant on the outside. We are now 1 to 9 u squared du. So we take the antiderivative. We get 1/4 u cubed over 3 from 1 to 9. Then we get u cubed over 12 from 1 to 9. So what do students do right now? They take the 4x minus 3 and they put it back in here. It's a complete waste of time. Don't do that. Why can't you do that, by the way? If you put 4x minus 3 in here and then try to evaluate, you made a gigantic mistake because 1 and 9 are not x variables. They're u variables. So what do you do now is you go right to evaluating. But we're just going to use u, which is simpler anyway. So what do we get? We get 9 cubed over 12 minus 1 cubed over 12. That is going to give us, I think it's going to be 728 over 12 as a result, which reduces to about 182 over 3. Okay, so that would be the area under the curve 4x minus 3 quantity squared from 1 to 3 using the substitution method. So I find at the end of the semester, by the way, students who are probably exhausted from the class often don't know this well enough, and they confuse the you-know-what out of substitution rule for the two different types of integrals. You just can't afford to do that. In the next section, chapter 6, we're going to do one section in there. It requires that you know all this stuff inside and out, and if you are going on to Calc 2, and any of this is in any way weak, you're in trouble. Literally the entire class is integration, or the first part of the class at least. So make sure that you are very good with this when it comes down to taking the test and everything else. Let's continue and try some more problems where we need to use the substitution rule in order to evaluate a definite integral. How about the area under the curve 1 over x plus 3 from 0 to 2? Okay, so if this was 1 over just x, then we could have done this right away, no substitution. But because we have an x plus 3, we now must use substitution in order to manage this. So the only thing we could make our inner function would be x plus 3, and if we find the derivative of that, we get 1 dx, which basically means that dx is equal to du. It's pretty super simple. Okay, but remember, we need to find the limits of integration. So we have our integral. Right now we have dx is equal to du, which replaces the top, and u is equal to x plus 3. So we have that so far. But we need those limits. So we have u is equal to 2 plus 3. So 2 plus 3, which is 5. And we have u is equal to 0 plus 3, which of course is equal to 3. So our new limits are 3 and 5. Alright, then we can do our integration. We have the antiderivative of du over u, or 1 over u du, is the natural log of u from 3 to 5. When we evaluate, we just do the natural log of the absolute value of 5 minus the natural log of the absolute value of 3, which we can then just drop the absolute values and get this. There is one thing I do want to point out, though. I'm actually not going to write. So this is fine as an answer, but ideally you want to return to your pre-calculus roots. I know that sounds funny, but basically we'd like to condense this into one natural log. It would look a whole lot better. And if you remember, when you take the difference of two logs, it's the same as division. So this is actually equal to the natural log of 5/3. This might be unfamiliar to you in terms of remembering, but it is the same thing. This is really the preferable answer, and it does come up sometimes I think in a lab it might come up, but that is what I would like you to put, but I'm okay with this too. Okay, so similar to the previous integral examples, I wanted to give you another denominator one here. So note that it appears that our u substitution is identical. It appears that when we take the derivative, that is also identical, but when we find our u's, we have different limits of integration. So we're going to have u equals -1 + 3 and -2 + 3. And that is going to end up giving us limits of 2 and 1. All right, so what is that the same as? So we got 1 and 2. We have that our dx is equal to our du, and we have now x + 3 is u, but we have a third here. Okay, so note that, and the reason why I'm putting these next to each other again is that these are two totally different scenarios. So if you're looking at this problem, we can't bring this, if we brought this u up to the top and made it u to the -1, if we tried integrating u to the -1, we would get u to the 0 over 0, which is a complete debacle. That's because you can't integrate that, and it's the natural log. But for u cubed, what we should be doing is changing this into u to the -3 du. Okay, once we have that, then we can integrate and get u to the -2 over -2 from 1 to 2, which is the same as -1 over 2u squared from 2 to 1. So we can then just evaluate. So we're going to get -1 over 2 times 2 squared minus -1 over 2 times 1 squared. If we do that, it looks like we're going to get -1/8 minus a -1/2. When we do plus there, we're going to get 3/8 as a result. So this is the area for this particular problem. These are unrelated. Again, we have very similar looking problems between these two, right? It's just, obviously I changed the limits, but that's not a big deal. It's just the denominators. You just have to remember that single variable natural log, if you have a higher degree, then you're going to be going in a different direction. More and more examples. What about the area under the curve for sine x over 2 from 0 to pi over 2? So remember, just this is 1/2 x. It's the same thing. Students often confuse this. Just remember those are the same kind of setup there. So it appears that our u is going to be our inner function, which is x over 2. But because it's 1/2 x, that means the derivative is just 1/2 dx, because the derivative of this is just 1/2. So if we multiply both sides by 2 of this, that means that 2 du is equal to dx. All right. So if we move on and talk about our limits are going to be u is equal to pi over 2 divided by 2, and u is equal to 0 divided by 2. So remember, I'm just taking these and plugging them in here, right? That's all, just plugging them right in there. So I get my u's are pi over 4 and 0. So my new limits, my u limits, to be very specific, are going to be that. This 4 can come on the outside. And we're going to get sine. We have u is going to replace x over 2. And we're going to have 2 du replacing dx. All right. Moving on. So this 2 can go to the outside and get 8 integral 0 to pi over 4 of sine u du, which means we can now take our antiderivative. So we're going to have 8. If we take the antiderivative of sine u, we get negative cosine u. And we're evaluating that from 0 to pi over 4. We can move this negative on the outside, so this thing is actually going to be negative 8 cosine u. Save a step here. So therefore, we can leave the negative 8 on the outside and just do cosine of pi over 4 minus cosine of 0 as our results. So this should be second nature. Remember, pi over 4, we're taking the x-coordinate in the first quadrant, which is root 2 over 2. Cosine of 0 is 1. So in the end, we're going to get negative 8 times the quantity root 2 over 2 minus 1. We can distribute that and not get anything nasty. So we're going to get negative 4 root 2 plus 8. And that is the exact net area under this curve. We've done a couple like number 17 already. We do have a sine and a cosine here. So this is a very interesting one, and I'll explain why. If we're going to do our u substitution for this, then we're going to set u equal to one or the other. Now note that neither one of them is a higher degree, so it doesn't really matter from that standpoint which way we go. Maybe we want to concentrate on the easier derivative. So for example, the derivative of sine is exactly cosine, where the derivative of cosine is negative sine. So maybe we want to remove the negative from the equation and just make u equal to sine x, which means du is equal to cosine x dx, and dx is equal to du over cosine. Okay? If we move on to here, then we can, again, similar to the last problem, we can move the 4 on the outside. Our sine becomes u, our cosine doesn't go anywhere, and we multiply by du over the cosine of x. Thankfully, these wipe out. And in the next step, we'll have a very nice equation, but what about those limits? So our limits are going to be u equals the sine, so here, the sine of pi over 4, if we plug in x, the sine of pi over 4 is root 2 over 2. And if we do the sine of 0, we get just 0. So our new limits are 0 and root 2 over 2. If we move on to the next step and rewrite this, we're going to get just u du sitting right here. We can then integrate, so we're going to get 4 times u squared over 2 when we integrate our u. We're going to evaluate that from root 2 over 2 to 0. We can then, if we'd like here, we can make this easier for us. We can make this just 2u squared, which means we can leave the 2 on the outside. And we can just evaluate root 2 over 2 and 0 at u squared. So we're going to get root 2 over 2 squared minus 0 squared. We want to do this little math here. So root 2 over 2 squared is 2 over 4, which is going to give us, it looks like a half. So this is a half minus 0. So if we do 2 times a half, believe it or not, this entire thing has an area of just 1 instead of a weird answer. But that is what you get as the area under the curve. So just to point out, remember, the key in all of these is deciphering in the beginning between the earlier methods, remembering to change the limits and not to substitute back in. That's obviously going to be a big deal in terms of learning and making sure you understand. Let's do these 2 remaining ones just because why not for these. These are definitely are more challenging to students than the indefinite integral ones, so worth doing for sure. 18, so we're looking at, in this scenario, we have 2 possible inner functions. We have a numerator and we have inside the denominator. By default, we usually pick the larger degree, so let's see how this goes. If we find the derivative, we're going to get 2x plus 4 dx. And if we divide, we get dx is equal to du over 2x plus 4. All right, what about our limits? So we're able to, at least we can look at this and say, all right, we got what we need for our substitution, but we need those limits. This is going to be a little bit more involved because we have a very large polynomial here, a second degree. We're going to plug in 3 squared plus 4 times 3 plus 7. That looks like it's going to give you 9, 12, and 7, which is 28. So that's pretty big. And then we're going to plug in 1 squared plus 4 times 1 plus 7. And that is going to give us, it looks like, 12. So this is going to be 12 and 28. We have our x plus 2 isn't going anywhere yet. We have the square root of u, and then dx is du over 2x plus 4. But, again, it doesn't appear that we have anything canceling out unless you think a little deeper and you take out a 2 and make this 2 times x plus 2. Then these will wipe out, and you will be able to move on. So we'll end up with a constant right here of 1/2 on the outside. We have a root u in the denominator. So basically you're looking at this, root u, and then a du here. But if we have a root u in the denominator, we don't want to leave it like that. We want to make sure that we change that to a decimal. And the decimal value is going to be u to the negative 1/2 du. Why? Because it's u to the 1/2 in the denominator, we want to move it to the numerator. So a lot of stuff going on here. Alrighty. So we have to take the integral. So 1/2, we take the integral of u to the negative 1/2. So as an aside here, this is going to be u to the negative 1/2 plus 1 over negative 1/2 plus 1. And negative 1/2 plus 1 is just 1/2. So we're going to end up with u to the 1/2 over 1/2, 12 to 8, 28. And if we invert that, we're going to get, so this right here, let's do that on the side. So this is going to end up being 2u to the 1/2, but the 2's are going to wipe out. So the whole thing is actually just going to be root u to the 1/2 from 12 to 28. If you evaluate, you're going to get root 28 minus root 12, which is an okay final answer. Do not change that into root 16. Again, don't give your professor convulsions. That is a poor algebra mistake. You could simplify. That would show good knowledge of algebra and get 2 root 7 minus 2 root 3 as your final answer. And this is exact as your result. So this one is, there's a lot of sort of little stuff that went on, here and here, canceling. Like, you could have gone into a lot more steps with this, but you should know your algebra and doing the little stuff, so you can sort of quickly go through it if you need to. Okay, the absolute last problem here is one of my favorites. Caution to that, right? If it's his favorite, then it's probably going to be hard. Not necessarily, but if you look at this, again, this is the type of problem that's going to give students the shakes. So let's say you were finding the area under the curve natural log of x cubed over x, already crazy, but you're evaluating from 1 over e to e. Okay, so, another one of those problems that looks just awful, but it's going to turn out to be very straightforward. So let's see how this goes exactly. What appears to be a good inner function? Hopefully the natural log of x kind of screams at you, which means the derivative of that is 1 over x dx, and then multiplying both sides by x, we get x du equals dx. All right, we go to our values over here. We get u cubed. We have an x over here that stays put, and then our dx is x du. Luckily enough, our x's will cancel out like they should and we will get a nice result. But we need those limits. So the limits are going to be, interestingly enough, the natural log of our top limit, which is the natural log of e, and it's going to be the natural log of 1 over e. Okay, natural log of e is an identity. It's equal to 1. And interestingly enough, we can change this into the natural log of e to the negative 1. Now, that is also the same as negative 1 natural log of e, because whenever you use nat logs, whatever the exponent is here, you can immediately move to the beginning. And since we already know this is, that is an interesting bracket. Since we already know this is 1, then this whole thing is just negative 1. So we have, in our scenario, this is negative 1 and this is 1. So, bringing down, negative 1 of 1, u cubed du. We can integrate. We're going to get u to the 4th over 4 from negative 1 to 1. Therefore, we can sub this in and get 1 to the 4th over 4 minus negative 1 to the 4th over 4. And something very interesting happens here. These both end up being positive 1/4, so you get a big fat goose egg 0 as your answer. So the net area, the exact net area for this is going to be literally 0. Okay, so we're at the end of the section. I did a trillion examples, so you should have plenty to study through and make sure you understand. Again, this is one of the most important sections there is, especially combined with 5.3. Going through those sections and knowing integration, if you're moving on, which is usually about half the students I see, this is just everything you're going to do in Calc 2. You got to know this. This is like the prerequisite material. If you're not moving on, realize that this is a gigantic part of your third exam and your final. And in order to move on to the very final section we're going to do, 6.2, you have to be able to do this as well, or it's going to be very painful for you.